Hello, welcome to Chapter 4, Analyzing and Representing Relationships Between Numerical Variables. In Chapters 2 and 3, we studied how to analyze one numerical variable. We used graphs and measures. In this Chapter 4, we are going to analyze the relationship between two numerical variables. We will introduce a new graph, the scatter plot, and two new measures, the Pearson's correlation coefficient and the determination coefficient. These are measures of how strong a linear relationship is. Let's go over the concepts as we solve exercises. Exercise 1. For each of the following scatter plots, describe the direction, shape, and strength of the relationship between the explanatory and the response variables. Here we have new vocabulary. First, in this context of correlation and regression, it's common to call the explanatory variable predictor and the response variable predicted variable. A scatterplot is a graph in which we have two axes. We put the explanatory variable in the x-axis and the response in the y-axis. Each individual in the sample has one value for the explanatory and another value for the response. These values are used as Cartesian coordinates and the individual is represented somewhere in the plane. For example, in this study, we had a sample of 30 drivers. Each driver has a value for h, which was the explanatory variable, and a value for visibility distance, the maximum distance at which this driver was able to read signs. This was the response variable. Each of these 30 dots represents one of the 30 drivers in the sample. For instance, this driver was around 32 years old, and his or her visibility distance was a bit more than 400 feet. This was the youngest driver, approximately 17, and this was the oldest driver, around 81 or 82 years old. This was the driver with the largest visibility distance, almost 600 feet, and these two were the drivers with the shortest visibility distance, less than 300 feet. A scatterplot helps us see the relationship between two numerical variables much faster than any other tool. There are three aspects of a relationship that you are expected to be able to describe quickly by looking at a scatterplot: the direction, the shape, and the strength. In this case, the direction is negative because this trajectory goes down. In more proper terms, the greater the values of the explanatory variable, the smaller the values of the response. In this case, the older the driver, the shorter their visibility distance. It is linear because a line would be the best fit for this cloud of dots, this data set. And it is strong, or fairly strong, because the dots adhere to the line pretty well. Let's try to do the same with the other graphs. This is clearly positive, it goes up. It's nonlinear, we see here a curve. More precisely, this looks logarithmic. It is strong because the dots adhere to this logarithmic pattern very well. This other graph is also positive and nonlinear. This looks almost perfectly exponential. We can call it very strong. Indeed, this is the number of bacteria a long time. It's well known that in these cases the exponential model is very appropriate. This is positive in the first half and negative in the second half. You can describe it this way or just say that there is no direction as a whole. It's nonlinear, it looks parabolic or quadratic if you prefer. It is strong. If you draw here a parabola, you will see that all the dots are close to it. This graph is very interesting because many people answer wrong. A typical answer that I hear is this relationship is slightly positive, linear, and very strong, because the dots adhere very well to the line. Maybe you could make a case on the first part, that this is slightly positive, but certainly we call this neither linear nor strong. In fact, here there is no relationship. In general, a horizontal line, as well as a vertical line, means no relationship. A horizontal distribution means that the y stays the same all along the spectrum of values of the x, so the y has nothing to do with the x. In this particular case, we see that the weight of newborns stays in the same range, around 3 kilograms, for all the different weights of the mothers. We can double check this by looking at the extreme values. This was the thinnest mom, 80 pounds, and her baby had a pretty average weight, more than 2 kilograms, far from being the thinnest baby. In the other extreme, we have here the heaviest mom with 250 pounds, more than 3 times as heavy as the previous mom, and her baby was also pretty average, seems like 3 kilograms and a half, also far from being the heaviest baby. In fact, the heaviest baby, 5 kilograms, and the tiniest baby, less than 1 kilogram, as well as a variety of other babies, were born to pretty average moms. So the best description of this relationship is no relationship. If we are to fill this out, maybe we can say direction none, shape linear horizontal, strength very weak because there is no relationship. In this last graph, we do see a positive direction and the best model seems to be a line. I don't think any curve could do a better job, but the strength is little. This is a weak relationship. Up to now, we have described strength qualitatively. Now we are introducing a measure of strength for linear relationships, what we call the Pearson's correlation coefficient or simply correlation coefficient, usually denoted with R or the Greek letter rho. In this course, we will use the R. It is a number whose absolute value goes from 0 to 1. The closer to 1, the stronger, and the closer to 0, the weaker. It also has a sign. The sign matches the direction. Let's practice this by assigning these correlation coefficients to the graphs at the right. -1 needs to be a relationship as strong as it could be, a perfect mathematical line, and going down. It's clearly this. -0.8 is still strong and going down. You may think of this, but I don't think this is strong enough, especially when we have here a graph that's clearly stronger. This is the -0.8. -0.5 is precisely this other one. -0.2 must be vaguely negative. So negative but very weak. It must be this. Do you see here that there is a little bit of a negative direction, but very weak? Let's go now to the other extreme. 0.9 means very strong and going up. It has to be this. 0.7 means fairly strong and going up. It must be this. 0.3 means vaguely positive. So positive but very weak. It must be this. Do you appreciate here the little positive direction? And the last one is 0. 0 means that a negative line would work as well as a positive line, and both lines would work badly. It must be this. Here a line like this would be as good as a line like this. This is the example of correlation coefficient 0. Exercise 3. Consider the graphs in exercise 1. What would the correlation coefficient approximately be for the bottom left graph? Since we agreed that this relationship is strong, a common mistake here is thinking that the correlation coefficient is close to 1. Notice that here a positive line would be as good as a negative line. Both would be bad. Therefore, the correlation coefficient is going to be close to 0. What about this other graph? Since we agreed that this relationship was not linear, a common mistake is thinking that the correlation coefficient would be small. Indeed, it will be pretty high, probably around 0.8 or 0.9, because we can draw a line here and the data points will be very close to it, which brings the next question. Is any of those correlation coefficients meaningful? Not really, because the Pearson's correlation coefficient is meaningful only for linear relationships. Exercise 4. Which of the following distributions will have a higher correlation coefficient? Very often, people answer the distribution in the right because the dots are closer to the line. The problem is that they are not. The catch here is that both distributions are exactly the same. these two individuals are these two individuals. This loner here in 65 is this loner here in 65. In the right, we just zoomed out. This is a good moment to say that the correlation coefficient does not vary if we change the scale of the axis or the units. Imagine that this is age in years and this is height in inches. Now we express age in months and height in centimeters. The new graph might look different, but the correlation coefficient will be exactly the same. That's why we say that it is unitless or dimensionless. It also does not change if we add a constant to all the values. To finish this part, let's talk about the flaws of the correlation coefficient. We have already mentioned that it applies only to linear relationships. We can mention more limitations in the context of exercise 5. What's the point that Frank Anscombe made with his famous quartet? Here we have the quartet. If I tell you that the dataset has a correlation coefficient of 0.82, probably you will think of something like this. The problem is that these other distributions also have a correlation coefficient of 0.82. Here we have a strong linear relationship, but here we have a strong non-linear relationship, and here it is even worse. We don't have relationship at all. Remember what we explained before about horizontal and vertical graphs. If it wasn't for this outlier, the correlation coefficient would be 0 or wouldn't exist. This single outlier pumps it up to 0.82. So another flaws of the correlation coefficient are: first, it needs to be supported by a scatter plot. It alone is not enough to infer shape. Second, it's easily alienated by outliers or small changes in the dataset. Here you have another example. If it wasn't for this outlier, the correlation coefficient would be 1. But this outlier drops it to 0.82. Going back to Anscombe, the genius of this quartet is that the other main measures that we have studied in this course have also the same values for these 4 datasets. The average of the x's here is the same as here, here, and here. The average of the y's here is the same as here, here, and here. And the same is true for the standard deviation and the variance. In other words, looking at the main measures of center, spread, and strength, these 4 datasets are undistinguishable. But when we graph them, we see that they are totally different. The point that Anscombe made in such a dramatic way is that graphs are paramount in statistics and data analysis. We shall not trust only measures. We must complement the measures with graphs. Finally, I want to mention that the regression line is also the same for the 4 datasets. The regression line is the new concept that we study in the next part of this chapter.